Alright, so this is question 3 from the Wiley homework number 7 ungraded. So the question is, it says, starting with a appropriate alkyl halide and base outline the synthesis that would yield the following alkene as the major or only product. So here's the alkene that they give us. And then they give us a bunch of bases. And they're all in protic solvents, right? So they give us sodium hydroxide in water. They give us potassium terbutoxide and terbutanol. They give us ammonia, which is just a solvent. There's no base there. And then they give us ethoxide, sodium ethoxide, and ethanol, right? So a few things that we should know about this. NaOH it's a strong unhindered base. It's pKa, it's acidic, it's acidity of its hydrogen. The pKa of its its hydrogen. The hydrogen that would be attached to the hydroxyl group is 15.7. Meaning, okay, so it's 15.7. So potassium terbutoxide is a strong hindered base, right? And the acidity of its hydrogen, the hydrogen that would be attached to, if it was terbutoxide, this hydrogen, its pKa would be 18, which means that it's less acidic than the hydrogen from the hydroxyl group. All right, we said that ammonia is not a base, so we're not going to be using that. And sodium ethoxide, if we had CH3CH2O, the hydrogen that is attached to the ethanol, before it became ethoxide, the pKa equals 16. So, and it's a strong unhindered base. So with the the potassium terbutoxide has a pKa of 18. Since it has a higher pKa, it means that it's a stronger base, right? It's the strongest base. sodium ethoxide with a pKa of 16. Well, it's sodium ethoxide. Its conjugate acid has a pKa of 16, which is lower than terbutanol, but higher than water. Water is the conjugate acid of hydroxide. So it's higher than water, lower than terbutanol. So it's the medium base, right? It's the medium base. And then that leaves water being, or hydroxide, the hydroxide ion from here being the weakest base. All right, so now using that information, we're gonna look, we need to start with an alkyl halide. And where we're gonna put it is, you know, we want, looking at what we want, right? This is what we want. We want the double bond to be 1, 2 away from the methyl group. So here's the methyl group. So we want it to be 1, 2. It has to be either here or here, and this is symmetrical, so that's pretty easy. So if we put the bromine right up here, we have a hydrogen here and a hydrogen here. Doing an E, so we're going to do an E2 elimination, right? We want E2 elimination to make a double bond. The question is, which one do we use, or what would create the only? Now the answer is sodium ethoxide. It's sodium ethoxide because Ch.7.WP.UG.3, sodium ethoxide, is more basic. Okay, it's more basic, so it's more readily able to pluck off these hydrogens, right? It's going to go either path A or it's going to go path B. Whatever path it takes, it's going to give us the molecule we're looking for. Right? Now it's sodium ethoxide rather than sodium hydroxide. It's sodium ethoxide rather than sodium hydroxide because sodium ethoxide is more basic than sodium hydroxide. So this is can more easily pluck off these hydrogens than this. I guess that's the logic behind it. And then potassium terbutoxide would have difficulty deprotonating the hydrogen from the second degree carbon, right? Both of these hydrogens are on second degree carbons. They're both attached to 2 other carbons. So due to steric hindrance, because potassium terbutoxide is a bulky base. And then maybe also, this is just like a theory or whatever, it could compete with SN1 because this potassium terbutoxide probably could maybe take these hydrogens off, but it would be very, very slow, and in that process So in order to answer this question, see question 2 in this series, and it's at the end. It's a Y option to not an answer. Okay, this is so potassium terbutoxide, this bulky base, probably could remove one of these hydrogens, but it would be very slow. And during that very, very slow process while that's happening, perhaps, maybe, the terbutanol that the potassium terbutoxide is dissolved in could self-protonate, right? And then could self-protonate, and then it would lose a water molecule. So then you would have water. You would have water, and then if you had water, then perhaps the bromine could float off by itself, and then you'd have a positive charge here, and then the water could come in, and it would be an SN1 reaction. That's just a theory, though. So that's that.